Hello everyone. It's Sunday, and what better way to cap the week than with some programming? So let's do some Advent of Code. For those of you joining us at the middle, Advent of Code is a series of programming challenges that runs between 1st and 25th of December. Every day we get a new challenge, and this challenge has two parts, but we can only see part 2 after finishing part 1. We've been solving these on the day every day so far, and it's been going pretty great. The story this year is that we're trying to save Christmas by fixing the snow machine, and we've been traveling across an archipelago of mostly floating islands, trying on a bit of a scavenger hunt to get components to fix said snow machine. I think today we'll be going to an iron island where we'll get components to fix the machine that creates the sand that's then used to filter the water that then feeds into the snow machine. The story is quite involved, but doesn't matter much. The interesting thing about Advent of Code is that the difficulty tends to, historically speaking, the difficulty ramps up over the days. So people frequently use this as an opportunity to try programming in some new ways. They try something different. For me, this year I'm trying to stream it. Also, I'm trying to solve Advent of Code using Elixir in Livebook. This here is Livebook. It's a web application. It lets you intersperse text and code, and after every code block, it executes it and outputs the result. So for example, this is our solution for part 1 from yesterday. We have the bit of code, and then Livebook executed it and showed us the result. And then Livebook has fancier features. So for example here, the result of executing this code is that it generates a text area in which we can paste our input in. Then a bit later, we can read the text from the input. And yeah, I think this is nicer than just writing the examples and the full inputs as comments in the source code, or just having files scattered around the file system. This feels much more readable. If you've ever used Jupyter notebooks, this is kind of like that, but with probably less features, but also much saner semantics. Specifically, Livebook always executes from top to bottom, and since it's Elixir and there's no global state, or rather there's no mutable state in general, the execution is always top to bottom. There's no chance that a cell further down affects a cell further up. But enough about this. Let's see what Advent of Code has in store for us today. So, Day 10, Pipe Maze. You use the hang glider to ride the hot air from Desert Island all the way up to the floating metal island. This island is surprisingly cold, and there definitely aren't any thermals to glide on, so you leave your hang glider behind. You wander around for a while. Oh, I just realized that since we're going with hang glider, this is probably more of a riff on Tears of the Kingdom and Zelda in general rather than One Piece. Well, live and learn. So, you wander around for a while, but you don't find any people or animals. However, you do occasionally find signposts labeled hot springs, pointing in a seemingly consistent direction. Maybe you can find someone at the hot springs and ask them where the desert machine parts are made. The landscape here is alien. Even the flowers and trees are made of metal. As you stop to admire some metal grass, you notice something metallic scurry away in your peripheral vision and jump into a big metal pipe. It didn't look like any animal you've seen. If you want a better look, you'll need to get ahead of it. Scanning the area, you discover, oh, we're literally just going to be chasing an animal now. Christmas is not going to happen this year, is it? Okay. Scanning the area, you discover that the entire field you're standing on is densely packed with pipes. It was hard to tell at first because they're the same metallic silver color as the ground. You make a quick sketch of the surface pipes you can see, your puzzle input. The pipes are arranged in a two-dimensional grid of tiles. Pipe is a vertical pipe connecting north and south. Dash is a horizontal pipe connecting east and west. L is a 90-degree bend connecting north and east. J is a 90-degree bend connecting north and west. 7 is a 90-degree bend connecting south and west. F is a 90-degree bend connecting south and east. Dot is ground. There is no pipe in this tile. S is your starting position. S is the starting position of the animal. There is a pipe on this tile, but your sketch doesn't show what shape that pipe has. Based on the acoustics of the animal's scurrying, you're confident that the pipe that contains the animal is one large continuous loop. For example, here is a square loop of pipe. Yes, this is indeed a square loop of pipe. If the animal had entered this loop in the northwest corner, the sketch would instead look like this. So it's the same as above, except one spot in the pipe is replaced by the letter S, the starting location. In the above diagram, the S tile is still a 90-degree F-bend. You can tell because of how the adjacent pipes connect to it. Unfortunately, you can tell because of how the adjacent pipes connect to it. I wonder if this is always the case, or if you can have pipes that are just connected incorrectly. Unfortunately, there are also many pipes that aren't connected to the loop. This sketch shows the same loop as above. Okay, so we cannot maybe we can still infer the shape of S, given that these pipes point away from S? In the above diagram, you can still figure out which pipes form the main loop. They're the ones connected to S. Pipes those pipes connect to, pipes those pipes connect to, and so on. Every pipe in the main loop connects to its two neighbors, including S, which will have exactly two pipes connecting to it, and which is assumed to connect back to those two pipes, O. And based on the pipe combinations we can have, there's no three-way split, as in there is no T-junction of any sort. So every pipe is always connected to exactly two other pipes. So our main loop is actually just a loop, it is not a maze. Here is a sketch that contains a slightly more complex main loop. So here we start with S and then go down, down, right, up, right, right, up, left, up, up, left, down, right, down, and then left again, and we end up back in S. Here's the same sketch with the extra non-main loop pipe tiles also shown. Right. So S still just has only two pipes connect. S still has only two pipes pointing at it. But here we can see that there is a pipe that is connected to nothing, and then a pipe that connects to the wrong side of our main loop. So it is possible to have pipes it is possible to have incorrectly connected pipes. If you want to get ahead of the animal, you should find the tile in the loop that is the farthest from the starting position. Because the animal is in the pipe, it doesn't make sense to measure this by direct distance. Instead, you need to find the tile that would take the longest number of steps along the loop to reach from the starting point, regardless of which way around the loop the animal went. In the first example with the square loop, you can count the distance from each tile in the loop. You can count the distance each tile in the loop is from the starting point like this. Unsurprisingly, the opposite corner is the furthest tile. In this example, the furthest point from the start is 4 steps away. Here's the more complex loop again. Here are the distances for each tile on that loop. There. Find a single giant loop starting at S. How many steps along the loop does it take to get from the starting position to the point furthest from the starting position? Okay, I'm just going to say this right now. This is actually a trick question. You don't have to actually find this giant loop. You just have to start at S, find the loop. Well, I guess you do have to find the loop, but then also count the distance in it. And we don't have to infer what S is. We can just presumably try to flood fill from it and see how we get back. Get your puzzle input. What does the full puzzle look like? This. So this is maybe a couple of hundred. This is a couple of hundreds on the side and a couple of hundred lines from top to bottom. This is not that many nodes. We can just iterate through them. So here's the plan. We're going to first read our input because the parsing is a bit tricky. We're not going to do anything special during parsing about the starting location. Later, after we do the parsing, we're going to start at S and then flood fill from it to compute the maximum distance. We're then going to keep track of... Yes, and then once we find what do we want? Yes, we're going to flood fill from it in a breadth first search sort of way. And then this is going to possibly go down wrong paths, but at some point we are going to reach a cell from two different directions. And then the depth of that cell is going to be our maximum. So let's start. Let's start part 1. We're going to create a new notebook. Let's call it AoC 2023 day 10. Let's now save this to avoid any surprises later. First off, we're going to need Kino as a dependency since we'll be using the Kino. The first section is going to be called helpers. And we're going to have multiple examples today. We can use Kino input text area to generate a text area where we can paste in our example. Then I believe we have a second example as well, and then also full input. Finally, the full input. Let's now copy paste in our examples so that we don't have to worry about this later, so that we don't have to keep switching between tabs. That was the simple example. Here is the complex example. Finally, our full input. Create a new section and call it part 1. So the first challenge is going to be to actually parse our input. So let's start by reading it. Now we have a new line we have the new line where the lines are separated by the new line character. So we string split this on new line. We now have a list with each line being an element, but we also have an empty string at the end because we had an empty string in our input. Let's trim. Now we just have the lines of the maze. Now I'm wondering, do we want to parse this as a graph Or do we want to keep processing this as a matrix of special characters? I feel like we want to turn this into a graph. Then we can even use, and then we can even use something fancy in Livebook and display it as a mermaid chart. So first we're going to parse this as a graph. First we need to annotate the lines with their line numbers. Then we're going to map over every line. Are we going to map? No, we're going to reduce over every line. And we're going to start with an empty map, which is going to be our grid, stored as a map. Then we take our line and our grid so far. And here it's not quite our line, it's our line and the index of our line. Next, we're going to map over every character in our line. So we start with line, then we do... Is there such a thing as a string map? There is not. So string to char list first. This turns it into a list of characters. With Elixir, so tuples have curly bracket syntax. Okay, so now this turned one of our lines into a char list. So this is actually a list of characters now. Since it's a list of characters, we can do enum reduce on it. And we start with our grid. Then we take... In fact, we're going to need an index here as well. So enum with index 0 again. Right here we have char, let's call it ch, and j. And then grid is our accumulator. So now we want to update grid with this particular character. And for this character, we want to store which other grid locations it connects to. So we case over ch. And if this is a dot, then we just return grid. And now if we run this, it should error out because we're not matching other characters. Yes. So what other characters do we have? We have... Start like this. So we have pipe. If we get a pipe, then we want to put single element into the grid. It will be at location I and j because this is the location of this character. Then it will be a list of two things, which will be the coordinates 1 above and the coordinates 1 below. So it will be I minus 1 and j, and I plus 1 and j. And this isn't quite right because this will probably let us go outside of the main play area, but we can filter it. We can filter out the invalid coordinates later. So we have pipe, horizontal bar, this one connects to j minus 1 and j plus 1. And I see we're going to have a lot of these map put grid ij calls here. So let's instead let's pull that outside. Connections. And then our connections here is empty list. And then we're just going to do mat put grid I, j, then connections. Now here, we can just return the list instead of having to do the call every single time. Okay. Next one was L, if I remember correctly. So this one connects I-1 and J to I and J plus 1. Then is J, and then we have J and 7. J. This connects above and to the left. Next we have 7. This connects below with to the left. This connects below and to the left. Next we have F. This connects below and to the right. Above here I used curly brackets instead of square brackets by mistake. We've already down ground, and then S is a starting position. I'm just going to say S connects to all four, X connects to all 4 directions. Okay. This should now parse. This generated something, but I have no idea if this is good or bad. So how do we do this? Let's move this into a new module called parse. Let's move this parsing into a new module because we'll be using it repeatedly. So def module, let's call it AoC, def read input. And this function is going to take a Kino input called input. It's going to do this whole thing. Here, instead of reading example 1, we read input. This should compile. It does. Now we can replace the whole call here by read input example 1. AoC.read input example 1. Okay, this worked. Let's create a new section here. Let's branch it off from helpers so that we don't have to compile part 1 every time. Let's call it experiments. Here, we're first going to read input example 1 again. Good. And what we want to ultimately do is generate a mermaid chart of this so that we can actually see a graphical representation of what we parsed. We're going to need the mermaid docs. We're also going to need Kino shorts mermaid. So we're going to call this function like this. Right, so graph top down. Let's say E. And do we have semicolons? Yes, we have semicolons. And then we pipe this into Kino shorts mermaid. This generated our graph. Now we want to turn this sort of our big map output into this. So Kino read input. We pass this through an enum map. No, first we pass this through an enum filter. And the filter is going to take the key, which we don't care about here, and the connections. Num empty cons. Yeah. And this is in fact not a filter, this is a reject. So now we should only get the nodes that have non-empty connections. Next, we map this. Our key is going to be an I and a J. But then we have connections. And then we're going to return something for each connection. So we need another map here. It's going to be CI and CJ, our connection. And then we're going to output a string that has I. So let's say n j, and then 2 dashes with no spaces. This points to CI and CJ, and then a semicolon. And I don't know if the spaces are important, so let's add 2 spaces as well. Now this gives us almost what we want. Finally, we need to do an enum join, and with new lines. Okay, and now we have, there's no new line here, let's add a new line here as well. Oh, this needs to be a flat map. Right, now we have all of the graph, connections. We don't have, however, the header. So how do we add the header? We assign this to some variable. Call it cons. Do graph ud and then cons. If we pipe this into Kino Shorts Mermaid, we should get a graphical representation of our example. Really, this is what our example actually looks like? Example 1. So our starting location connects to 2 nodes. No, this should just be a single loop. This is our starting location. Why does it think, oh, it connects to N01 because I said our starting location, where are we? Here. Our starting location connects indiscriminately towards all its surroundings. Okay, so let's ignore this for a second. This is clearly wrong and this is clearly wrong. Now these ones, should they be connecting both ways? They should, because from one you can, where are we? From here you can go down, but then from down you can go back up. Our pipes are not directional. Okay, so the immediate problem is that we're connecting our starting location to too many places. But that's fine, because if we then, when we actually do our traversal, we'll go here and this will be a dead end. So this won't actually affect our logic in any way. Okay, what happens if we do this on example 2? Here we have example 2. And now we see the little problem where we can connect to cells outside of our play area. But again, this doesn't really matter because these are clearly dead ends, so they won't be able to contribute to any cycle. I'm curious, if I do graph LR, is this any clearer? Yes, this is clearer. So where's our starting location for example 2? Example 2, our starting location is going to be 0 and 2, and 0, 2. This is our starting location. And we have n01 feeding into it, but not the other way around, which seems surprising. Zero one feeds into n01. n01 feeds into n02. Oh, this is not our starting location. Our starting location is n20. Where's n20? Here we go. Right. So I think that our parsing is good enough. It's not actually correct in the strict sense of the word, but I think it's good enough for the algorithm we're about to apply. And the algorithm we're about to apply is flood fill starting from the starting location. Then we're just going to spread out sort of to the left through these nodes, right through these nodes as well. If we spread into the offshoot here at the top, it won't matter because this will terminate very quickly. Same goes for some other random offshoots here. How is n14 pointing to them but not the other way around? Oh, because this is an incorrectly installed pipe. Right? n14 is incorrectly installed. n14, actually more readable here. n14. Yes, no? Is this even our example? One that starts with 7. No, this is a different example. They have so many examples for today. This is our example 2, n14. No, it should be connected properly to n04, but it's not. Because that's not 4, is it? This is not 4. This is 4. Right, so this points to n13 and n24, but neither of them connect back to 4 and then 1, 3. All right, so parsing is correct. We flood, so back to the algorithm. We start at n20, this is our starting location, then we flood left and right. We search the graph. And where's our actual loop? How do we get back? So our actual loop goes something like this, and then loops back through the top here, back to n02. Okay. So we're going to need a recursive algorithm. Do we want a recursive algorithm? Yes. We want a recursive algorithm that keeps track of where of the current node, that keeps track of the set of current nodes we're in, and then expands into all of their neighbors. And it also keeps track of which nodes we've visited so far. And then whenever we reach a node that we've already visited, we add its length to the possible max loop lengths. And so our main loop is this big thing. But strictly speaking, we could also say that these two nodes are a valid loop, right? Because you can go from n20 into n30 and then back. The only problem with these two is that they're not long enough. Well, I don't know if the actual problem statement would allow this, but they haven't ruled it out. So let's get coding. We have our input here. Then we're just going to pipe. Let's get one more thing from our input. Let's get the starting location. So here, where I said we start with the grid, we start with the grid and then also nil. And then we have the grid and start. So our accumulator is now a tuple of 2 elements. Then here, again, we start with the grid. You have the grid and also the starting location. And here we have the grid and the starting location. And at the end, we return the grid and the starting location. Actually, here, it's going to be if character is start, then we return this location instead of this is going to be our starting location. Else, it's just going to be start. We pipe all of this. This just gives us back. Oh, this gives us both our grid and our start, so it should be fine. Did I forget a comma? Parentheses are required to solve. Sure, I need to add parentheses. Let's do this on 2 lines. Okay, this compiled. Does this still run? It does something, and now it also returns our starting location. So here. Where's read input? There's probably some way to color the starting node in Mermaid, isn't there? But we're just going to ignore that. This is going to give us cons and start. We're just going to ignore start and keep on doing the thing we've already done. Yep. Okay, so now we have starting input. We have our connections and our start. So we're going to call a function. Let's call it part1. Let's call it reverse. And it's our list of the list of nodes we're currently in is start. Then we also take cons. And I have to put this in the module because Elixir doesn't like functions defined at the top level. Current cons. Right. We also need a map set. We're going to need to pass in a lot more arguments to this when we actually do this traversal. So let's say this traverse calls our lower level traverse. And this one is also going to take a map set new. Visited. And I realize now we don't actually want a map set because we'll need to record the depth. So this is going to be just a map. I'm going to just split it off on its own line here because we're going to add a bunch more arguments. Okay, so we have depth traverse, current visited, connections. We also need the current depth. The current depth is 0. Right, we now have traverse, visited, and depth. So next up, we need to traverse all of the neighbors of current. Actually, we have to enum through current, I believe. We might have to do a different operation instead of enum, probably reduce. Yeah, we would probably have to do a reduce. Let's just do that. Visited. And it's going to be per node visited. The first thing we're going to do is check if current node has already been visited. It has been visited, then we don't do anything and just return visited unchanged. I'm just going to write the flood fill first, and then we're going to figure out how to do the loop thing later, because it's too many things to juggle at the same time for me. So if we've already been visited, then we're done. We don't have to do anything further. If we haven't visited the current node, then first we add current node to visited. At the depth we're currently at. Then we're going to recurse through all of visited's neighbors. So unknown.reduce visited fn, and here we do cons of per node. And I believe current node will always be in cons because we're even including the bullshit connections here. So, yeah. Well, no. Because we're including bullshit connections, cons might not, the current node might not actually have any connections. Or current node not in cons. I wonder if we can actually write this in Elixir. We're going to find out. Okay, cons of current node. Actually, we can do this in a much nicer way. Here, we're going to do map get, and we're going to pass the default value. Map get from cons. We're trying to get the current node, but then if we don't have the current node, we just return an empty list. So this line always returns the list, and then we can reduce over it. I realize now that the way I'm writing this, I don't actually want to do multiple traversals, do I? I just want to add more elements to current and then call traverse just a single time at the end. So reduce here doesn't reduce just over visited, it returns over visited and our next level of current. Next, yes, let's call these our next nodes. So if current node isn't visited, then we just return next and visited. We make no changes. Otherwise, we add the current node to visited, and then we return we return the new next nodes are going to be next const with this, with all of the connections for the current node. And then we just return next and visited. And now this at the end we should call traverse again. But instead of that, let's just run this once and see what we get. So we call traverse and then we get next nodes. So we visited just one. Yes, we visited just one node, which is our starting location, 1, 1. And then we have the 4 possible connections for 1, 1. Okay. So here I have just say next and visited is this. Then we just call traverse instead of current of next, then the new visited. then the depth has increased by 1 and the connections remain unchanged. And our base case is going to, the base case for our recursion is going to be when current is empty, when there are no longer any current nodes. In that case, we are just going to return visited. This is taking too long, so I screwed something up. Let's debug this. I'll put s depth. Let's just print out current. I'm guessing what's happening here is that we probably need to check if the next node is in visited or not somewhere. Oh, let's see what this prints. Stop. So, at depth 0, we have visited just 1, 1. At depth 1, we have visited at the depth 1, we are currently visiting all of the connections from the starting node. At depth 2, we are visiting 4 more connections. At depth 3, we are visiting a whole lot of connections. This just seems wrong somehow. Then at depth 4, oh wow, we're just adding more and more and more. And also I see a 1, 1 here. So what's going on? From 0, 1, where can we go to? From 0, 1, we can go to nowhere. From 2, 1, where can we go to? From 2, 1, we can go either back or forward. So from 2, 1, we can go to 1, 1 again. And this added 1, 1 again here. There's probably a nicer way of doing this, but let's just filter this list here by nodes that haven't been visited yet. Split this up across multiple lines. A parentheses somewhere in here. I'm missing an end somewhere in here. It's not called list reject, it's called a num reject. This is still taking too long. But now we should get... Oh, that's interesting. It didn't reject it properly. It didn't reject it at all properly. I'm just confused about how membership in a map works. Well, the great thing about Elixir is that we can test this out. So let's create a map that looks a lot like what we have. Ooh. Right, so we have our map. Now, what happens if I do 1, 1 in map? False. So presumably, the thing that would actually work is 1, 1 full in map? Yes. Okay, so checking if a map has a key this is not the correct way to check if a map has a key. So map has key, map 1, 1. returns whether the given key exists in the given map. Okay, so map has key is what we want to use. So if map has key kernode visited kernode. Here again, if map has key, and I bet we don't actually need to do this reject here anymore, but I'll delete it after I see that it actually works. No, we'll delete it after we see that it works. Map has key, there's a question mark missing here. Okay, this now terminated. So we started with 1, 1, then we went into 4 possible directions, but only 2 of them continued. So then we end up with this visited map. And indeed, this was the opposite corner, which is at max distance 4. I claim here that I don't actually need to do this reject. This should also work. This does a few more repeated steps, but that's fine, because computers are fast. Here, I can just join this so that it's simpler code. We no longer need the comment, the debug print. Okay, so now we have a visited. We now have are actually flood-filled map of visited nodes. So these are all of the nodes that are reachable from the starting node and the distance to them. The problem is that we don't know which of them are in a loop and which aren't. So I believe I need to, in addition to depth, I should also keep track of how many times we've reached a given node. Is that correct? Oh, I think I'm just getting confused here. Because every node is sort of a loop. Unless it's broken. Right, so the example, let's just make our own example here. Let's call this example 3. So first off, let's start and make a very, very simple loop. This one here is F, no, L. This one is J, and here we have a dot and then a pipe. So this is an example. If I print it, this should just be a loop and nothing else. Yes. So the way we break this one is we add a new line at the top. Then here we do a 7. No, I want something that points to the right, so an F. And then here we do dot dot, dash dash. Now if I draw this, you should see the problem. Yeah, so starting at N10, which is our starting location, we can go here, we can go into N00, then N01, then N02, and then presumably N03. Let's see what happens with our flood fill algorithm if we run it on N03. So do we end up with, yes, we end up with N034. So we end up with the bogus node at a distance 4. But this is not part of a loop. This is not part of a loop, so we shouldn't be considering it. So in addition to tracking the depth for each visited node, we also need to track how many times we've actually encountered it. I believe that will help. Where are we here? Where is... Here. This is where we add the visited... This is where we add the current node to visited. So here we're going to depth 1, because we've only encountered it once. Then here, if we've... And then here is where we've ended up in the node a second time. If we've ended up in the node a second time, we are going to update visited current node. And we actually need an update of some sort. What does update take as an argument? It takes existing value. Right, it takes existing value and then returns a new value, as expected, I guess. So this one takes depth count, and it's going to return same depth but count plus 1. Let's not call this depth so that we don't get confused. Let's call it D. So when we encounter a node the second time, we increase its count, its visited count by 1. This should work. Update 3 is undefined. It's update 4. We need a default value, but the default value can be fake because it will never actually be hit. We know it won't ever be hit because we've checked that the current node is in the visited map a bit above. Okay, now this is a bit better maybe. So this was our bogus node, and we see that it has only one connection leading into it. And our actual starting position, 1, has 4 nodes leading back into it, as expected. And then everything in the main loop has 2 nodes in it. So now we just have to filter out all of the nodes that have exactly 2 connections in them, because that's the main loop. Filter fn. And I, in fact, don't even... I just need enum.values. Map.values? Map.values, because I only need the results. I don't actually care about the node names anymore. We don't care about the node names anymore. So now we can just do our random filter, fn. We don't... In this case, we don't care about the depth, we just care about the count. And we want our count to be 2. So these are the depths in our main sequence, in our main loop. Now we can just do enum.map. We can use the short version, the short function syntax here. And lem of 1 and 1. No, this returns the counts, which are always 2. So we want to return this, which is the depth. Now here we just do enum.max, which is 4. And that's correct. And now in our more complicated example 2, the answer should be actually 1. It's still 4. And in the more complicated example, it's 8. And the question is, how many steps along the loop does it take to get from the starting point to the points furthest from the starting position? So now, what happens if we run this on full? It took a worryingly long amount of time to evaluate, but should be fine. That's not the right answer. Your answer is too low. If you're stuck, make sure you're using the full input data. And also, there are general tips in the About page. We're not consulting the About page. Okay. So let's debug. Hypothetically, what if something loops back into our main loop but doesn't reach out of it? As in, what happens if our main loop has a connection count of 3? That could happen. But that's not what's going on here. I'm not going to actually try to draw the main loop because that's going to be way too big. We debug this. So the max here is, let's print out more things about our full example. So 6082 was 6918 is what I thought was the example, but it wasn't. Okay. Let's just print our visited. What does this look like? It's a big input, and there are many things. I think this is the main loop. What do we have here that isn't in the main loop? Num.filter. Is there a map.filter? There is a map.filter. Presumably we take key and the value as a tuple. The key is uninteresting, the value, the depth is uninteresting. The count, however, I'd like to see all of the elements that are not 2. What does this look like? Right, so this is important. We've just found out that in the big input, basically everything is part of the main loop, and only 3 nodes are not part of the main loop. Maybe 2213. So this whole thing is just one big loop. Out of curiosity, where is the starting location? I'll inspect start. Starting location is 22114. Oh, that's interesting. So our starting location has a depth of 0, which is unsurprising, and then 3 connections coming into it. So why is this? This is because from 22114 we go into 113, but this should lead back, and 22115. So 113 and 22113 and 22115 are clearly adjacent to this. So these are clearly the two neighbors that are not part of our massive loop. But why is the number of visited 3? It should be 4. Before, because we go from the starting location into this one, and then we should loop back. And we go from our starting location and we should loop back, but clearly we did not loop back once. We looped back once, but not twice, rather. Okay, so I would like to print out in our traversal function here, not here, if cur node is 22113, 22114, 2. And so let's just print here visiting start. There are indeed 3 visiting starts. Okay, let's IO inspect. What are the connections to start? There are 4 connections to start as expected. Now, what if we check the connections to 22.113, which is one of the nodes that is not part of the main loop. So the connections to 22.113, the connections to 22.113 are 21.113 and 23.113. Because we go from the starting node, then we go into this one, but then this one doesn't loop back because it's badly connected. This explains how, and presumably for the other one, it does loop back. Right, so if we look at 22.115, 22.115. 22.115. This also doesn't loop back. That's interesting. Our starting location. We look at the full puzzle input. Where is S? Here it is. So S, I incorrectly said it goes left. Ah, so the problem is that, okay, so there are 2 different problems. The bigger problem with the logic of what we wrote is that the thing adjacent to the starting location might be its own loop, but not the main loop, which is what's happening here. The other problem is that S has 3 incomings, but how can S have 3 incomings? Must be just a coding error. So we definitely don't go into it from either left or right. We can only go into S from top or bottom. But presumably what's happening here is that we go from S left, which is incorrect, but then we go top, right, and then back into it. Okay, so I'm getting confused by all of the bad connections. So I think the solution is to just not have bad connections. Right. So after we've read our input, we're going to filter it for everything that's bad. Yes. How are we going to filter it for everything that's bad? For every connection, we're going to check both ways, and if the connection doesn't work both ways, then we just eliminate it. So here we do another enum reduce. Is this an enum reduce? No. This is cons and start equals this whole thing. For some reason, I didn't work there. Okay, cons. And now we're going to filter cons. Or rather, we're going to map over it. We're going to do a map. What this is going to return. So we pipe cons into enum dot map. Surely there must be an enum map values or something. Elixir documentation. Then here we have map, the map module, summary, keys, merge, new, put new, replace. There is no map. So I guess we're going to be turning this into a list and then back into a map. So enum.map. Then we take node and cons. Then we're going to filter the cons. Going to filter the cons, or we're going to filter the cons. We start with cons, then we take other node, then we get another node, and if cons of if map.get of cons and other node if node in. So this is it. We're going to filter the connections for only connections that also loop back to us. Here we return node and cons. And surely this needs to be enum.into. We need to convert it back into a map. Then we return cons and start. Now, if we print this, we should get rid of at least... We should get rid of at least some of these nodes. Inspected the map, got... Where is this? Line 33. Line 33. I'm overwriting cons here. Let's call this one neighbors. 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 Okay. Right. Now we still have this offshoot because the offshoot is actually correct. And then we have the main loop as well. But now if we change the example so that this offshoot is not correct anymore, we now have a horizontal pipe. We should just not have the offshoot anymore now. Well, we have the offshoot, but it's a separate graph from our actual main one. Okay, and now if I run it here, I should only have 2 visiting starts. Still 3. 22114 is reachable by 3 nodes. How does this even happen? Well, let's print it out. So, instead of printing it here, let's print it here. Here. So, if this contains the starting node, then we print. This is called neighbors. Let's just have that code there. These are the neighbors. We add the neighbors here. Now, if 222114 is in the neighbors, then we print it. Then we print visiting start from current node. Start gets visited one extra time because it gets called. Yeah, because it's the initial node. Okay, so that mystery is solved. They're only visiting it from the node above and the node below, which is correct. We only visit it from the node above and the node below. All right. So now if I uncomment everything else, we get 0. So something broke somewhere. I was filtering by nodes that are different from 2 here, which was clearly wrong. Okay, 6923, which is greater than our previous answer. That's the right answer. You have 1 gold star. Okay. So my original assumption that we can just parse the graphing correctly was wrong. And we pay the price for it by getting confused somewhere in here. Let's comment out. Let's just quickly comment out our put S and our IO inspect here. Still 6923. All right, let's see what part 2 is about. Long problem statement today. So, part 2. You quickly reach the farthest point of the loop, but the animal never emerges. Maybe its nest is within the area enclosed by the loop? Determine whether it's even worth taking the time to search for such a nest. You should calculate how many tiles are contained within the loop. For example, so this loop goes down, then does a little Ankh shape, and then, or a little light bulb shape, and then goes back. The above loop encloses merely 4 tiles. The 2 pairs of dots in the southeast and southwest corners, marked I below. Okay, so these are the enclosed tiles. The middle dot tiles marked 0 below are not in the loop. Here is the same loop again with those regions marked. In fact, there doesn't even need to be a full tile path to the outside for the tiles to count as outside the loop. Squeezing between pipes is also allowed. Here, I is still within the loop and 0 is still outside the loop. So, because even if we squeeze between the pipes like this, we still end up enclosed. In both of the above examples, 4 tiles are enclosed by the loop. Here's a larger example. The above sketch has many random bits of ground, some of which are in the loop and some of which are outside of it. This larger example, 8 tiles are enclosed by the loop. Any tile that isn't part of the main loop can count as being enclosed by the loop. Any tile that isn't part of the main loop count as being enclosed by the loop. So other loops don't matter here, only the main loop matters. Here's another example with many bits of junk lying around that aren't connected to the main loop at all. Here are just the tiles that are enclosed by the loop marked with I. This example, 10 tiles are enclosed by the loop. Figure out whether you have time to search for the nest by calculating the area within the loop. How many tiles are enclosed by the loop? This feels a bit like the opposite of the original problem. Whereas before we were walking through the pipe, now we want to walk between the pipe, or we want to walk through the tiles outside of the pipe. Since we know what the main loop is, we can just draw it out on the grid. Then perhaps we can do this operation on the grid itself. The trouble here is that we can squeeze between pipes. So even just drawing out the grid isn't quite sufficient. Or is it? Because we know that the main loop is a loop, so it fully encloses something. If we were to do this manually, how do we figure out that this is a bad square? So a square at the edge is obviously a bad square because you can just go outside with it. You can just reach outside of the grid with it. This square is a bad square. Why? You can't go left, right, or about or top with it. You can, however, go down. Why can you go down? You can go down because there is a downward pointing pipe. And following the downward pointing pipe, right, so the reason you can't go right here is because this is a downward pointing pipe. This is a vertical pipe, not a horizontal pipe. So you can't go through it. From here, we can go outside because we're following vertical pipes, or we're following pipes that have openings downward or above. So downward isn't sufficient. Any pipe with a vertical opening can be traversed vertically. And any pipe with a horizontal opening can be traversed horizontally. So this eye here, we can't go left, we can't go right, we can't go down. We can, however, follow the chain of vertical pipes up. Then we can follow the path of horizontal pipes to the right. Then we can follow the horizontal pipe, the vertical pipes down. Then we end up in this new enclosed space. But why can't we follow, once we're here, why can't we follow the horizontal pipes to the left and then the vertical pipes outside? That's because we're on the inside of the pipe, not on the outside of the pipe. Oh dear, so we have to keep track of which side of the pipe we are on. This feels suspiciously tricky, so I'm wondering if we've missed something. We could explode the graph and just triple actually turn every cell into 9 cells, and then we can just code up, then we can just use similar logic to code through this. And we take every cell and then we explode it so that there are 9 cells of it now, and the middle is just whatever pipe is in that cell. And then we also have on each of the cross points either a pipe or a dash. And if we do this, we'll have 2 spaces between these two we'll have 2 spaces between these 2 pipes, and we'll be able to go up. And then we'll have 2 spaces between the top and bottom pipes, so we'll be able to go right and then down. But we still won't be able to escape because we'll have the barriers. Then once we do this particular, then what? We can do this sort of flood fill and see if we manage to escape and get to the edge or not. And if we do manage to get to the edge, we can just backtrack and make those nodes uninteresting. Well, we don't even need to backtrack. We can just start from the outer edge and then work inward, and then count all of the cells that we haven't reached. For example, there are 10 tiles enclosed by the loop. How many tiles are enclosed by the loop? This is frustratingly complicated. Oh, and of course, we only care about the main loop again. We don't care about any other loops. But we also know that there aren't any other loops in the big example, don't we? Do we know that? We don't know that for sure. Okay. So question 1. Let's do the simple thing. Let's see what's the difference between visited and connections. So have we visited all of the nodes? That's the question. Let's start a new section here. Let's call this part 2. Then we copy all of this, and then we be playing with it. So here we have visited, right? Yes, we just have visited. So what's map.keys of visited? What's the length of this? That's a big length. What's the length of cons? Not a list. Of course, it's not a list, it's map.size, map.length, size. No, it has to be enum.length because it's an enumerable. There's no enum.length. How do I find the size of a map? the lazy thing and I turn it into keys again. Keys, and then length. Okay, so we did not manage to reach all of the nodes that have connections. So there are definitely some nodes out there that are not part of the main loop. Presumably they still block motion. Right? Do they block motion? Well, we care about nodes that are constrained by, that are within the main loop. So here, about nodes that are in the main loop, but not... Let's just hope that there's only one main loop and then we figure it out later. If that doesn't work, we try something more complicated. So do we do our exploding grid idea, or do we do something else? I don't have another idea, so let's do the exploding grid thing. So let's define a module, R2, do, and explode. This takes a grid. This takes an actual grid. Part 2 and Part 1 are going to share very little code, which is slightly frustrating. Yeah, we're going to do Part 2 completely graphically. So Part 2... Okay, first off, we're going to need something to read the grid in a way that we can process nicely. Kino, this is going to be a Kino input. Then we're going to read text. Here, we're going to do part 2 with grid of example 1. Start with example 1. Okay. Next, we split it into lines. Split. And we also trim. Next, we turn each of these into a char list. Now, then we map. We take each line. First we turn into a char list, then we turn into a tuple, so that we can index into it efficiently. Now we have our grid. Next, we're going to define a function that explodes a grid. How does this work? For every... we pipe this into part2.explode. So we start with a grid. This being a list is unhelpful. So we're going to turn the whole input here into another bigger tuple. Did this work? Yes, this created a new tuple, a tuple of tuples. And iterate over a tuple. Don't know. If I do 1, 2, 3, can I do enum.map over this? No, enumerable is not defined on tuples. So we don't turn it into a tuple yet. We now just have a list of lists, a list of char lists. Okay, so we have a grid. We're going to enum map over the grid. Well, it will be a flat map because we'll be generating multiple lists for each grid line. Fn line, and then for each line we again do an enum flat map. It has to be a flat map because we'll be generating 3 characters for each character. No, it is not going to be a flat map yet. And here, depending on the character, we're going to output different things. So if we get a dot, then we're going to output dot, dot, dots, dot, 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 and dot. So these are 9 dots. Then if we have an L, it's written like this, then the middle one is going to be top, the middle one is always, this one's going to be L, then this one is going to be a pipe to the right. I think this is going to work. Although the starting position is going to be annoying. Yeah. There's just a pain to... This isn't even all that hard, it's just annoying to write. So if it's an F, then the middle one is an F. And then have a dash here and a pipe down here. And if it's a 7, then the middle one is the 7. It's always the middle one is always the same. And pipe down. And then if it's a J, then we have a pipe to the top, then a J in the middle, and then a right dash here. If it's a vertical pipe, it's vertical pipes all through the middle. The horizontal pipe, and it's just horizontal pipes in the middle, on the middle line. And if it's an S, what do we do? As we're kind of screwed unless we already know what the main loop is. But we do know what the main loop is. Rather, we know we have the clean version of the input. We should be able to tell if S go in which direction S is actually supposed to go. Let's just write it like this and let's leave a comment that this isn't correct. This isn't correct. Use the clean input. And in fact, can we just generate this from the clean input? This actually raises more questions. If the pipes aren't connected, presumably you can just sneak past them? As in, the pipes... Maybe it doesn't matter? Let's just do another example. This is F, this is dash, this is 7. Can we go up through this across this pipe here? Well, it doesn't matter because we're outside of the main loop. Let's do a more convoluted example. I want this example. Now my question is, what happens if we have a dash here? Can we go through it? In fact, there doesn't even need to be a full tile path to the outside for tiles to count outside of the loop. Squeezing between pipes is also allowed. Here I is within the loop and O is still outside of it. Does this example have something useful? So these are clearly outside of the loop. They're not interesting. This is also outside of the loop apparently. Why? Because we can just sneak through between the pipes like this. And this one... Can we? No, we can't sneak through here, so where do we sneak through? Go down here. Well, we can't go left, so we must go right. Is this... How does this not reach the outside? No, how does this reach the outside? So we have to go down. Oh, then we go left. Then we serpentine like this. But then we get stuck here. Where is it? Here we go. This will make it easier to look at. So how does this get outside? We can't sneak through here because these are connected. We can't sneak through there, so we must be sneaking down below through here, between the 7 and this L. So we are now here. From here, we cannot go left because this 7 is blocking us, so we have to go right. So we get to here. Then we can't go any further right because this is blocking us, so we get to here. From here, we just sneak through between these two pipes and we're just outside. Because there's nothing blocking us between these two positions. Okay. I still don't have an answer to my question of whether a badly connected pipe blocks passage through. But I think the answer lies here. Everything outside of the main loop in here it said everything outside of the main loop. I think that's the important bit. They are just types that are enclosed by the loop. Whenever the problem says the loop, presumably it refers to the main loop. Part 1 also consistently says the loop. Along the loop. Fortunately, there are many pipes that aren't connected to the loop. Form the main loop. Every pipe in the main loop connects to its two neighbors, with some extra non-main loop pipe tiles. Well, if the assumption is that we can't... Okay, so if the assumption is that tiles outside of the main loop don't matter, then we just shouldn't draw them because that will just make everything more complicated. We should just draw the main loop and see what's within it. In that case, we shouldn't be processing the input as is. We should instead be starting with the sanitized input and then drawing out the main loop on the exploded board. Then we can flood fill across the expanded board. Okay, let's do this. So this whole grid thing here is wrong. We instead want a draw grid of some sort. The draw grid. And it takes... What does this take? This takes cons and start. Here we do part 1. We do AoC read input, what it's called, right? AoC read input. Then we just pipe this into part 2 draw grid. For starters, let's just return cons in draw grid to see that this compiles. It does. I think I'm just going to store the grid as a gigantic map, because we're going to be modifying it repeatedly, and Elixir makes modifying maps easy. So draw grid is actually going to first generate a map from 0 to how big is my actual grid. So we start with cons, then we do map keys, And then we want to compute the maximum of either of the two numbers. So then we do enum.map fn. This takes the tuple of an I and a j and returns the list of an... No, then we just do unzip, don't we? Then we do map.unzip. So these are all of the indices we have for our two... for our two indices. These are all of the values we have for our two indices, so we just want the maximum of each list. So then i's, j's, ivals, jvals, and then we're going to return max list.max and num.max. Num.max of ivals and num.max of jvals. Then missing an end here. Okay, so it's 4 and 4. This is going to be called imax and jmax. And we could have probably computed this by counting lines or something, but I'd rather just do everything on the same data or on the same input to avoid surprises. So now 0 to imax times 3 minus 1. And we can actually use a 4 here, can't we? I takes values from this, j takes values from 0 to jmax times 3 minus 1 as well. We're accumulating into our new grid. Then we just do map.put ij, and we assume we start with a dot. We put this into the grid. It's called into, it's called reduce. And this hopefully works. The largest numbers I see are 11. The largest indices I see are 11, which is about right. We're going to need to draw this grid because otherwise we won't understand what's happening. And grid. Module grid, let's do a data structure. Def struct. The data structure is going to take... It's going to take lines, calls, and then actual data. And we do enforce keys. We want all of these to always be given. Lines, calls, data. So draw grid here. This gives us the grid. Or rather, this gives us the data. This is no longer called imax, this is called lines. You know, it is imax. And then here we return a grid. If I run this, it will give an error because we haven't filled out the keys. Yes, so lines is going to be imax times 3, oh, minus 1. So let's just write it above here so that we don't duplicate. And calls is going to be jmax times 3. And here we have lines -1 because ranges in Elixir go to the very end, are inclusive on both ends. Here, lines is lines, calls is calls, and data is data. We don't need start here, apparently. But we do want to print the grid. Oh, and this isn't actually correct because we haven't actually, drawn the grid. We haven't drawn the grid yet. We've just filled it out with spaces. But let's do a print first. What do we print here? We are going to do 0, 2, grid dot lines -1. Now we can just use a for here. For I less than this, do. And for j less than, for j out of grid dot calls -1, I'll put s. No, we can't actually use the Cartesian product here because we're going to want to do something different on every line. Here we're just going to print out the one character. Here where I'm doing characters, I feel like I actually want to do strings instead, because that's easier to work with. Grid.data of I and j. And then after every line, we print out a new line. There's no grid. It's called grid. But after draw grid, we do part 2, print a grid. And instead of draw grid, we're going to call it make grid. As I output s, always write an empty line and a new line at the end. But adds a new, so we want right in fact. The right one. Right. Device stdio char data, yes, so we want right instead of put s. Okay, so now we have a grid, and this grid is 3 times bigger than the original. Yes. Now we are going to traverse the grid here. We're going to traverse the grid starting at start and draw something on it. We're going to call data is draw pipes of data, start, and cons. Start should in fact be a list, because you'll possibly be in multiple nodes at the same time. We have that. Draw pipes. Then this is data, this is current, this is cons, which is unchanged. Then we take current, then we enum map through it. Then we have a single function called cur_node. But it's not a map, it's a reduce, because we'll be modifying data as we go along. So cur_node and data. Now what do we do? We have a node, have a data, we will do different things based on the connections of the current node. So we're going to do several map puts over data. So map put data on the current node. If we've gotten to a current node, then this means that the center here is completely full. First off, we need to translate the current node to the new coordinate system, which is which is 3 times as big. So cur_node is going to be, instead of cur_node, we're going to do ci and cj. Then we're going to have gi is ci times 3 plus 1. Plus 1? Yes, this will be the middle of the new cell. And this is going to be cj times 3 plus 1. Let's just do map.put data of gi and gj to be hash. Let's say that hash is how we mark a completely blocked off path. And this whole thing is going to return our new data. So if I run this, it should put a single hash at the starting location. It should did. Nothing else. Right, now we have to do more, depending on the connections. Let's say here data is this, and then okay, now then we take the connections. Of the current node. This is going to be a list of 2 things, because it's part of the main loop. And really what we care about here is not what the values are, but how they are relative to our current node, as in if they're above or to the left and so on. So we pipe this into enum.reduce. We start with data, of course, and then we take neighbor I and neighbor j into data. Now we know that one of ni or nj is going to be the same as ci or cj, and the other one is going to be different, because we can only do movement across horizontals or verticals. So if ni is greater than ci, then we do something. Okay, we use a cont for this. We know that only one of these can happen, so we can just do it like this. If ni is greater than ci, that means we went down. So we're going to do map.put data gi plus 1 and gj. And this is going to be a hash again. Okay. If it was less than ci, then it's a minus here. Instead, we had nj is greater than cj, then this is unchanged, but then we have a +1 here. It's less than cj. If nj is less than cj, then we do gj -1. Okay, so if I run this now, it should add 2 more hash marks. This is example 1. So the hash marks should be to the left and below. The left and below. This has to be a tuple. To the left and below. Okay, so this drew it correctly. But now we have to recurse in draw pipes. And the recursion is going to stop when current is empty, when there are no more nodes to go through. In that case, we're just going to return data. This should still work. Yep, okay. So here, in addition to current, we have to actually, here we have to return 2 things. We have to return both next and data. Both next and data. Then we start with empty list and data. And here again we have next and data. And this whole thing gives us more data. Doesn't it? But it also gives us the next. This also tells us what to add to next. So that's incorrect here. So if I return next, and we're going to modify next in a second. Next. Once we've done all of this, we will... This is here. Correct, this should be 2 more spaces indented. Yeah. Okay, here, and then we do draw pipes of data, which has been updated, then of next, and then of cons, which never changes. And if we run this, it should still run. What happened here? 935. Oh, here, reduce on data, on next and data. This is not a great problem for functional programming, or rather for a purely functional language like Elixir. Okay, so now we have next. And then here we have to add something to next. What are we going to add? We're going to add just ni and nj. I think this is it, right? Because we start with the start, which is in the original coordinate system. Oh yeah, so we always just add the next node here. What am I doing? This is what it's supposed to look like. To copy it like this. Yep. And like this. And if I run this now, it runs for a really long time, so I screwed something up. The thing I screwed up is that it shouldn't, if the node has been visited already, we shouldn't visit it again. So this time we can just do a map set here. Where are we? If ci cj in map in visited, and we just return next and data unchanged. Else we do this whole thing. I'm going to check in a second if in works on map sets like I hope it does. We don't need this, whatever this was. We do instead want set new. If they want to, let's say this, let's say 1 1. This gives us a new map set, and now 1 1 in map set. True. Okay, so this should work. This should now terminate. But we also need to pass visited here. What we pass to visited, what we add to visited, we add all of the current to visited. New visited is enum.reduce. We take all of the current, we take visited, and we just do current node visited map set.put visited current node. We could have done this here, but this code is already pretty complicated, so we can just split it up. Alright, and now we have our nice little drawing of 1. And we can clearly see the nodes that are, of example 1, and we can clearly see the nodes that are contained within. Let's take this more complicated example as well. Example 4. Here we are at part 2. Let's look at example 4. Yep, and we have the drawing. Is it actually flush against the edge? Here, it's not flush against the edge. Right, but the way our input processing works is that we ignore any extra lines on the left, on the right, and on the bottom. That's fine. So here, we can clearly see that these are the spaces contained within. Because we can go around, all the way around. This one in the middle leads to the outside, so it doesn't help. Actually, we've got a better example, don't we? Yes, this is the better example for... This is the better example for because it has the trickiness in it. Okay. Now if I run this, no case matching 79. Where is this? It's 13. 13 in what? It just doesn't, read input doesn't work. What did I screw up here? Oh, I copied the one with the eyes. So we modify it. Well, we've got 4 dots here. 1, 2, 3, 4. Got 4 dots here. 1, 2, 3, 4. Got 2 dots here. Let's not do this. We can just make our input laxer. Here where we do read input, instead of doing this as the first case, we do it as the end case, and we do it for any other character. Now it should just work. This was... we need to print grid and make grid and print grid. Okay, so now the trickiness doesn't trick us, because we see that there is clearly space here. Alright, let's do one final example, which is this big, complicated monstrosity. Example 5, Kino input text area, example. Now if we do print grid here, if we print this grid, what do we get? Ugh, we get some complicated thing. Right, but notably this was, I remember this, so this was one of the O's that confused me. Just here. This O confused me and I didn't know how you could get out with it. You can get out with it by just going across the diagonal here. Is that the O that confused me? Yes, because we have this big hole here, and then a line, and then an O, then an empty space next to the line. So we have the line, and there, and the O is in the middle here. This is how you escape from there. Then from the one above it, there's also an O here, right? There's also an O here, and this one escapes by going between these pipes. And where are the eyes? There's a big cluster of eyes just a bit to the right of our O. This is the O, and then just a bit to the right should be a cluster of eyes, presumably here. Is it? This feels incorrect. It shouldn't just terminate like this, should it? No, the bottom here should be an L, so there's something wrong? Print function just wrong. The hell is this? So something's definitely wrong. Let's go back to -1. Let's actually print the line numbers, the correct line numbers. This still runs, but here we're going to do io.write I divided by 3, whole integer division. So this is line 0, this is line 1, and so on. Then we have 3 lines 8. Is this all our input has? Let's collapse part 1 so that we don't have to keep scrolling past it. So 8 lines. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We're missing a line. Yes, there should definitely be... We start from 0, so there should definitely be a 9. So what's grid.lines? Imax times 3. That's correct. So this is just not -1. Imax. Imax is the maximum value we saw. Is it just the case that this has a bunch of spaces? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9. So the Imax here is going to be 9, because that's the largest number we'll observe. And this is going to be 27. IO inspect lines should be 27. It's 27. So then we constructed the grid using from 0 to 27. Should be fine. Populated the grid. Then here. That's correct, this should be up to 27. Why is it not drawing? Is it just cutting off my output somehow? IO inspect grid.lines. 27. Now from 0 to 8 it is 27, but we want 30. Right, this is Imax plus 1. Right, because this is the maximum value, not the length. Okay, now it looks better. Now we have the final line. So now back to what we were looking at here. So these are the eyes here, which don't escape downward. So presumably this is the space, these are the eyes here, and they indeed do not escape downward because we end up in this little cul-de-sac here. Okay, so let's flood fill, I guess. The first off question here, why are there so many spaces here? I feel like there are a lot of spaces here. Because the actual square is this, this, this. And then why do I have an empty square there? So one empty square and then two empty squares above. One empty square and then two empty squares above. Is this thing just not part of the big grid? Definitely what I'm looking at. Right, this is example 5. Example 5. Okay, so we have a bunch of pipes here that are not actually part of the main pipe. Let's just see what a different version of drop pipes looks like. Let's write a version of drop pipes, let's call it drop pipes 2, that just draws all of the connections rather than all of the connections of the main loop. Yeah, draw pipes. This one's, in fact, much easier to write. So this is draw pipes 2. It takes the data, which is our little grid thing, and then it just takes cons. Then we reduce over the cons. Although this isn't quite right because this will still not contain the fake pipes, the pipes that aren't connected properly because we filtered those out earlier. So, okay, so not to do. Include bad pipes. Reduce. So we're going to reduce with data as the accumulator. Then we're going to take a CI and CJ, and then cons, and then data. Then we're going to return what? Then we're going to modify data in what way precisely? We're basically going to do the whole thing from above here. Well, without bothering with next and okay, so grid I is CI times 3 plus 1. Grid J is CJ times 3 plus 1. Then the data, we just put a little hash in the middle. Then we go over all of the connections. We don't have to bother with the next, we just have data. Have to bother with next, we just have data. And here again, we just delete off the next stuff. Then we put the hashes just as before. Let's try calling data with draw pipes 2 here. Variable start is unused. Yes, it is. Access module only supports... Where's this? This is line 58. Again, I misnamed these. But it should be neighbors. Didn't I run into this here? We go over, we reduce over the connections. Oh, and here we just don't reduce over connections. That's why we got away with it. Broken. right? Because here it's not neighbors, this is actually cons. Oh, in fact, I don't even need to look it up anymore. I can just use neighbors here. Let's draw something. What did it actually draw? Let's take the simpler example first. Right, so in example 1, clearly something's broken. Right, yeah, this should just be one square. I know start is unused. Stop warning me about it. The problem is that we're not actually checking if neighbors is empty or not. Because if we don't have any neighbors, then we don't actually have a cell. If it's empty, then we just return data without changing it. Otherwise, we do the whole thing. The error message, not compile module, undefined variable neighbors. H. Okay, now we have a square. Now if we try this on 2, what was 2 that it had something at the very bottom there? Example 2, this example 2 has something weird at the top and then something bad at the bottom. But we can't clearly see what's going on here because, again, we're filtering out this. We're filtering out the bad pipes. So let's pass an extra argument to read input. Include bad pipes. True. Here, opts. Include bad pipes is keyword.get opts. Include bad pipes. And by default, we will not be including bad pipes. This is kind of how you do keyword arguments in Elixir, or how you do named arguments in Elixir. You basically pass a list of options, and then you get the value out of the list. Okay, here. If include bad pipes, and then we just return cons and start. Otherwise, we do the actual filtering here. And this, the last secret here to doing keyword arguments in Elixir is you give it a default value of an empty list. This still runs. We don't care about part 1 anymore. Part 2. Okay, and now this should draw more stuff. And so at the very top, we have a 7, I guess. At the very top, we have a 7, and then a dash, and then an F. We have a 7, and then a dash, and then an F. And then at the bottom, we have this little U-shaped thing. So this will be an L, a dash, and then a J, L dash J. L, oh, no dash, just L and J. Yes. Okay, this looks good. Delete this comment because we fixed it. All right, now we try this on example 5, which was the tricky one. So now we have this hugely complicated input and it hasn't actually changed. That's frustrating. So this was not part. Let's look at this bit by bit. So there's a little space here between lines 3 and 4. So between lines 3 and 4, there's a space. Here's the space. And then there's a bunch of space adjacent to the edge above it. There's a bunch of space adjacent to the edge above it, yes. And then there's a little escape route going up. And indeed, there's a little escape route going up. And then on the other side of that escape route is a big fat O, which is like this is just an empty space. So it should be 3 by 3. But then we're going to have one more cell from the right side of this, and then one more cell from the left side of F. So this here should be 5 spaces wide. Oh, and it is indeed 5 spaces wide. This is the O. Right, and now what's above it? This is... Where's the actual... Where does... Oh, this is the O. This is the O. Then what's this? This is another O? No, this is not an O because it's too short to be an O. This is the bottom part of these. Yes. And then, oh, an F. Okay, so this is just a little escape route, but it's not actually a main cell. I know how to make this easier to debug. When we print the grid here, if div of I and 3, not div rem, and rem of j and 3 is 0, and grid data of I and j is a dot, then we're going to print it differently. So we're going to print empty spaces differently. We're going to do IO write, let's say at, and otherwise we're going to print the thing. And it's not 1, it's not 0, it's 1. Right, so now we can actually see where the empty spaces were. There's only one empty space here, and then there's another empty space here. And then there are these ones here. Okay, this is done. Or this is, we now have a nicely formatted grid in the form of a map. So now we're just going to flood fill it, aren't we? We're going to flood fill it and see how many basically I want to start from an empty space, so say this one, then expand outward. Really, I only need to do this from the edges. Well, let's write our own. Let's write the flood fill first, and then we see what we do with this. But today it's taking a really long time. So flood fill. We take our grid as input. This is just going to call the more complicated version of flood fill, which takes a grid, the nodes we're currently at. So let's say this also takes a starting position. Let's not call it start because we've used start for a different name later, previously. Let's just call it current node. Current node. Do we need anything else? What are we filling it with? Let's say letter. No, we're just going to fill it always with O. Okay. But if this is all we're doing, then we don't actually need the extra function. Okay, so we have current. We take all of the currents and whatever it is, it's going to return a new data for the grid. And we take all of the currents and we reduce over them. We start with grid.data. And as our function, we take, what do we take? We will have an I and a J. We're always operating in grid coordinates at this point. And the current data, and data. Now, if data of I and J is dot, we do something. This is the good. If it's different from dot, actually, we don't do anything. We just return data. And our next is going to be next, right? Here we have to iterate over empty list. We have to reduce over empty list and grid data. Here we do next as well. We pass through next as well. Okay. Now, if we reach the dot, this means, what does this mean? This means we're going to replace the dot with our letter, which is O. So grid is map.put grid I and J and the letter O, yes. Then we have to return the new next and then the grid. What is the new next? The new next is the current next, but with all of our neighbors added to this. So I-1 and J, I+1 and J, I and J -1, and I and J +1. And we have to handle the case where we're outside of the grid somewhere. Here, if. And how do we do this? We do map.get here of data, then we try to get I and J out of the map, and then if there isn't an I and J in the map, we return the default of dot. And then when we're outside of the grid, this will return a dot, this will the condition will be false, so we'll just not iterate into it. Okay, so now we have a next in the data. So we're going to do flood fill of we replace the data inside of grid, and instead of current we have next. And this whole algorithm, this whole flood fill stops when current is empty. In that case, we're going to be returning the grid. This should compile. Variable data is unused at line 89. That's concerning. Here. The data is replaced with the data, of course. Okay, and now if I do a flood fill starting at 0, 0, it should do something. R2.flood fill. It is the first argument, and then our second argument is the current, which is 0, 0. Yep, and doesn't terminate. But something is wrong here. Let's debug. IO inspect current. Stop. How did it get to -4? So clearly this didn't work. Right, because the only way to get to -4 is to get to -3 and then do... So it must have gotten into here at -3, which shouldn't be possible. Map.get -4 and -4. This is not in the map, so it will return dot. Here we should return question mark. Dot fetch undefined. Where is this? This is 980. 980? Line 80. Because this didn't return a grid? Surely this returned a grid. Grid fetch is undefined. Oh, so I must have passed the grid data somewhere, the grid as the data somewhere else as well. Where? Here we start with the grid data. Well, let's see what this returns. This whole function returned a grid, and then there's the data, and in the data is a grid. My kingdom for a statically typed language, or for a strongly typed language. Here. What's grid? This is data. This is data. And this is data. Do we have... It really shouldn't appear anywhere here. Okay, now it return... Now it... Where is this? What does it return? It returns a big grid. We should be able to print it. Okay, and now we have this monstrosity. We can get rid of the IO inspect. The grid, I keep noticing that it returns a list of OKs. Let's just return one OK. Okay, so now we have the thing. Let's try it on a simple example. Now we have the thing. And notice I did something wrong with start here, because we're including the bad pipes. We'll try it with both ways and see what happens. So we flood fill all of the outside, so anything that isn't outside by process of elimination must be inside. But it looks like it did the correct thing. If we try this with 2, it did the right thing. It didn't get confused about the little bit of piping at the bottom, and it didn't get confused about the bad pipes at the top, like the little unconnected 7 that was here. Okay, this seems to work. I forget what 3 was. Oh, 3 is the one where I just had one length of pipe at the very top that would block everything. And it did indeed block everything. Should it have blocked everything? And these pipes are definitely connected to each other, but should they be connected to the edges? Because I have include bad pipes. What happens if I do this? If I don't include the bad pipes, then this looks much better. Let's just quickly try this out again for 1. Works. 2. Works. It did not get confused by the stuff at the bottom. Three is the one we just tried. 4. What was 4? 4 was the little thing with like the lamp shape. This also did the right thing. 5. 5 was the super complicated shape. This also worked because, and it correctly found, yeah, it correctly went into the little hidey hole here. And the only things left are 1, 2, 3, 4, 5, 6, 7, 8. And 8 was the answer. 8 tiles are enclosed by the loop. Yes. Okay, so this appears to be working. I'm cautiously optimistic that this will work. Now, it's incorrect to just start from the... I think it's actually sufficient to start from the very top, because this isn't the real grid. This is our fake grid. So there's always an edge, there's always space around the edge. So starting from just one point on the edge is enough. We don't have to start from all points on the edge. Okay, so let's, instead of printing the grid, let's say count holes. Part 2, count inside. Count inside is going to look a lot like printed grid. Except instead of printing, we're counting. Okay, so first off here, instead of doing a 4, we're going to do an enum reduce. And we start with 0. This is going to be our count. Then we have I as a parameter, and we don't print anything. Now, inside of this, we do our j iteration again as a reduce. But this time we start from count, which was actually our second parameter above. And this takes a j and a count. And now this. So if it's a dot and it's in the right location, then we've increased our count by 1. Else, we do not increase the count. This should be it. This should be it. Grid.lines -1. Undefined variable I. Oh, yes, this is just the iteration now. 8. Okay, what happens if we do this on full? Takes a while and returns 320. That's not the right answer. Your answer is too low. Okay. So 320 is too low. What happens if I don't include the bad pipes? What happens if I include the bad pipes? Then we get 67 because we now have to deal with edges. All right, let's not going to print this. I'm going to look at example 2, I believe. Is this the one? No. See? This is the one. So let's start along all the edges instead of starting off at just in one location. No, that doesn't make sense. My answer was too low. Answer was too low. This means I incorrectly marked some pipes as inside. This means I incorrectly marked some pipes as outside when they were in fact inside. Really? And 20 too low. Can I even print full? Or is it too big? Probably too big. This is... Oh, it did print. Definitely printed. $320 is too low. Okay, but if I can print it, I can also flood fill it. There are indeed just a bunch of random bad pipes everywhere. Like this is definitely a section of bad piping. The only way I can imagine this happening is if it's too low, so I filled out too much space. So what happens if I have an example? Yeah, let's try something different. Construct an example. This is going to be example 6. What happens if I have an island in the middle? Okay, so this one is going to look like S and dash dash dash. I want 3 dashes. 3 dashes enough. Maybe. Let's do it like this. Here we're going to have F dash dash. No, an F dash 7. Close pipe down. Pipe. This is going to be an L, a dash, a J, vertical pipe, and here L, dash dash dash, J. So now we have a little island in the middle. Try this on example 6. What do I get? I get if I count this, actually let's make print return the grid. Now if I count this, it will say 0, but in fact, it should say like 6 probably, because there are 6 things here. Okay, so let's do the original thing. Instead of using draw pipes 2, let's use draw pipes 1, which draws only the main loop. Here. Instead of draw pipes 2, draw pipes 1. And define variable start. All right. Here. Now it's a 6. What happens if we run this on the other examples? On 1. This is unchanged, because there were no bad pipes. 2. It still works because it just now deleted the bad piping in the bottom right and in the top left. 3. This is just another square. It's 4. 4 is the lamp shape. And the lamp shape has 2 on either side, and it didn't get confused by anything else. 5. 8, because I guess there just were no bad pipes here. Okay, so we don't print things anymore. And we do the full thing. 5 to 9. 5 to 9. Oh, yes! Yes! That's the right answer. You are 1 gold star closer to restoring snow operations. Okay, done. So, I think the bigger problem today was that I couldn't really understand the question. Like this, the exact semantics here of handling bad pipes are very ambiguous. So we had to solve 4 different problems. We had to solve the problems with including bad pipes and excluding bad pipes, because we didn't know what they were expecting, and then we had to draw the grid, both including all of the weird pipes, all of the unconnected pipes, and not including all of the unconnected pipes. And even like this, we got the right answer, but I am not, this is not a general solution. I think the general problem is just ambiguous. Alright. I'm now curious, what do the stats look like? Surely... Okay, yeah, very few people are solving it. Usually this is more around 30,000. The people seem... The split between part 2 and part 1 is about the same, is about even. So people are indeed having problem with part 2. Not surprising, because like part 1 and part 2 seem like completely different problems. Well, that's not exactly true. So part 1 is a different problem as far as I'm concerned, because I solved it in the nicer way by turning everything into a graph with actual connections to the adjacent nodes. Whereas part 2 is a much more graphical thing. Yes, I could have done part 1 graphically too, but it still wouldn't have helped fundamentally, because, again, the traversal strategy is different. In part 1, we have to match on the character and then go left or right or bottom or top or above, depending on what the character is. But in part 2, we don't do that. Well, we do that when drawing the main loop. Yeah, in fact, having the proper graph generated in part 1 was good because that let us draw the main loop in part 2 easily. If we didn't have the whole graph, then drawing the loop would have been annoying. We'd have had to do some sort of exclusion logic, maybe, to exclude all of the pipes that aren't part of the main loop. I guess this is what I deserve for complaining yesterday about the simple problem. But this was not fun to write, and it wasn't challenging. It was challenging in a write the code sort of way, but it wasn't challenging in a mental way. Yes, it's sort of like, yeah, it's sort of like challenging in the same way as solving a maze is challenging, but not challenging in the way solving a riddle is challenging. Well, enough about this. Let's call it a day. I'm not going to try to refactor this because it's a mess and there's fundamentally nothing I can do to make it less of a mess. Right. Thank you for listening. See you all tomorrow when we do day 11.